Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from homework assignment 6.4. 6.4, what we're doing here is we're adding and subtracting like radicals. And so the idea here is one of the big ideas I think that really helps is if you think about them similarly to when you learned how to add and subtract like terms, you'll do much better. But let's start off with number one. It says two radicals are like radicals. What makes them like radicals? If each radical has the same index, so same index, and the same radicand. So of course the index is our n value. That's called our root index. And this value in here is called the radicand. Okay, so that's what they're talking about there. Now this is determine the following. Number two, determine the following equation is true or false. And that might look good, but that is actually false because only like radicals can be added. What rule is being broken here? Well, the actual index or indices, they are the same. That part's good. But the part that is not good is that we have different radicands. So we cannot add the two radicals together. That's false. Okay. So another thing I'd like to do before we start, let's see if we have any of them. Yeah, there's one right there. Let me kind of do some problems and kind of walk us back to memory lane, right? Like for instance, if we had a 2x, let's say plus, I don't know, 5y plus 6x. Now, when you first did something like that, you might have said, well, this means multiplication and that's multiplied. So, and it's true. That does mean multiplication when you have a number next to a variable. But it's better to think about it as a coefficient if you're going to add and subtract like terms. Meaning you want to think of it like this. How many x's do I have in this term? Well, I got two x's. And how many x's? See, the coefficient tells us how many of these things we have, right? So I got two x's there, and I got six x's there, so I have a total of, and you put that together, and you have 2 plus 6, that's going to be what? 8x. And why am I not going to add these y values with it? Because they are different, and they're not like terms. Now, you learned that in pre-algebra, and I claim that you already knew this about like terms even before this, because in the real world, if I take those same numbers, but I said, okay, I'm going to measure using my tape measure, I measure out 2 feet. I'm going to add that to 5 inches. And then I'm going to add that to 6 feet. If someone said, please add up those measurements, you wouldn't add up 2 plus 5 plus 6. Why? Because they are not like terms. They're not like things. This tells us how many feet we have. We got 2 feet there. And the coefficient tells us how many feet. We got 6 feet there. So we have a total of 8 feet. And you better not add that with you could say 8 feet 5 inches, but you can't add 8 and 5, right, and call that 13 feet inches, right? Because they're unlike terms. They will not add together. They have to be the same types of measurements, the same things. That's the same thing with x's and y's. And here we go. That's the same thing with like radicals. So I'm going to do a similar problem, similar numbers, but I'm going to use radicals. So I'm going to say, how about 2 square root of 5? Let me use another number since we already have a 5 there. I don't want to have any misunderstandings that way. But 2, let's say square root of 3 plus 5. And let's make this the square root of 7 plus 6 square root of 3. So just like my two previous examples, I'm adding like radicals. And we already know that like radicals, the indices have to be the same and the radicands have to be the same. But even if I just kind of say it this way, look at this is saying I have 2 what's. I've got 2 square root of 3's. And how many square root of 3's do I have over here? I got 6 of them. I have 6 square root of 3's. So those are like radicals. It would tell me how many square root of 3's do I have total. I have 8 square root of 3's. Now I can't add that with the 5 square root of 7s because those are square root of 7s. Those are something different, right? And so if you think about it like that, this section actually is not that hard because it connects with all your previous learning about combining like terms. Okay, so I encourage you to try to think about it like that. You can only add like things. Like things in the real world can only be added together. Multiplication is a little different, right? But so what do I have here? I have 4 square root of 3 and 2 square root of 3. I'm adding square root of 3's. So I must have, they're all like radicals, right? Square root of 3, square root of 3. So I have a total of 6 square root of 3. And so that's done. Over here, what am I adding up? Well, I'm adding up the like radicals are cube root of x. Cube root of x. Well, I have 7 cube root of x, and I've got a minus 3 cube root of x, so I've got a total of 4. What are they? Cube root of x's. Cube root of x. And if you want to go through and identify each one, that's fine too. The indices are all 2, so that satisfies that part. And the other part that needs to be satisfied is the radicands are all 5x. But in my mind, I see it as I got square root of 5x's. So I've got 6 square root of 5x minus 2 square root of 5x, which is 4 square root of 5x. Oh, wait, I've got more of them over here. So I've got 4 square root of 5x and 6 square root of 5x. That's going to total out to 10 of what? 10 square root of 5x's, or 10 square root of 5x. Okay, moving right along. Subtraction works just the same because just as long as you take your subtraction sign with you, this is something we had to learn back in algebra, that if you're going to move terms around, you got to take the signs with them because then you're really adding a negative, so you're allowed to move it then. But anyhow, I'm hoping we're okay with that. Let's look at the like radicals. I'm going to use some color. So I see cube root of 3. So I see cube root of 3's there, and I see more cube root of 3's here. But these other guys are not cube roots. These other guys have different radicals, or indices rather. And so those are square roots. So they are different. Even though the radicands are 3, it has to be the same exact thing that you're adding together, right? So I can see that when I add those together, I've got 4 cube root of 3's and 5 cube root of 3's adds to 9 cube root of 3. Now you see that we have more going on here. I've got, take the sign with it though. Don't forget the sign, I guess, yeah. So we've got, I was thinking about maybe I should put a box around it so you know I'm talking about the sign as well. You got to take the sign in front. I've got negative 6 square root of 2, so negative 6 square root of 3 and negative 3 square root of 3. So negative 6 minus 3 is a negative 9 square root of 3. And that is your final answer. 9 cube root of 3 minus 9 square root of 3. And those, even though they look like they are very similar, they're actually just totally, they're different. They are different. They're not like terms because this guy here is a cube root of 3 and this is a square root of 3. So you cannot add them together. And don't, yeah, that's it. That's all we have to do. They're not like terms. Let's try the next one. Add as indicated. Well, they're not like terms, right? Because this is, now they are square roots. So I got to give that to it, but the radicands are different. Now, the thing is sometimes they're actually kind of disguised, meaning if you can simplify a radical, meaning pulling out, in this case, perfect squares, and it becomes the same radicand and same indices, then you can add them together. And this is going to be an example of that. Let's take it to the right, equals. And I think I'm going to do a little bit of scratch work over here. 12 breaks down to what? 4 times 3? And you know 4 is 2 times 2, so that is just going to be 2 squared times 3 is 12. Maybe I'll actually write under it. Let's get rid of that. So 12 is the same thing as 2 squared times 3. And we all know, at this point that if the power matches the index, out comes that number. So this is now going to be, I'll pull that 2 out, and what do I have left inside the square root? 3 plus 8 square root of 3. Now you can clearly see that we're adding up square root of 3's and square root of 3's. So we've got 2 of them here and 8 of them here. Well, that's going to be 10 square root of 3. And we're done. 10 square root of 3. Next, number 8. In a similar way, we need to see, can we actually simplify anything? So I'm going to take 16, and I'm going to remember that's 4 times 4. So it does have a perfect square, but guess what we're looking for? You always want to start out by checking out what is the root index, because that tells you what grouping or what power you have to have for it to come out of a cube root. And you need a cube. So we need 3, and we only have 2. But wait a minute. 4 is 2 times 2. And that 4 is 2 times 2. I do have 3. I do have 2 cubed times 2. I do have a perfect cube. So I can rewrite 16 as 2 cubed times 2, right? That's still 16. Minus 7, this one's already simplified all the way, right? There's only 1 2 there, and you need to have 2 cubed for it to simplify out. So that's done. And like we said before, we all know that when we have a cube that matches a cube root, out comes that number, which was a 2. And so now we have 2 cube root of 2 minus 7 cube root. Okay, they're like radicals now. 7 minus 2, well, that's going to give me a negative 5 cube root of 2. Negative 5 cube root of 2. All right, add or subtract as indicated. Well, they're all 4th roots, so that's good. Indices are all 4. The radicans are all 2, so these guys are all like radicals and will add up. Once again, I guess I should highlight all the indices are 4, 4th root. All radicans are 2, so 4th root of 2. These guys are all like terms. Let's just go ahead and work it. We've got now what is in front of here. If I gave you an x, what would you say? What coefficient goes in front of the x? And if you said 1, you're right? We don't have to show it, but it's a 1. That's the same thing with radicans. I don't see any number in front of it, so that's really a 1, if that helps, right? So we have 1 minus 6. This gives me a negative 5 of what? 4th root of 2. And I've got 8 4th root 2. So negative 5 and 8 is going to be 3 4th root of 2. And we're done. 3 4th root of 2. Okay, let's go to the next one. So as you see, this stuff is actually not too bad once you get it in the right frame, in the right part of your brain, meaning thinking about it kind of like adding and subtracting like terms. Of course, you still have to simplify radicals, so that's the different part, but there's a strong connection on how the math works, though. So, like I said before, important to realize that these are, if you don't see an index, you know for sure these guys are considered to be square roots. So I'm looking for perfect squares. So if I'm going to do a little bit of work on this to try to simplify this, I think I've got okay space on this one. So let's just go right below it. And I can say that, what does 54 factor down to? I don't know. One possible combo is 9 times 6. Now remember, I want to get some perfect squares. Oh, wait a minute. Isn't 9 a perfect square, right? 3 times 3. So I'm going to write this as 3 squared times 6. And 6 is just 2 times 3, so that's not a perfect square, right? So at that point, I think what we can do is rewrite this as 2. And on the inside, I've got the 3 squared. Once again, I like to put parentheses around factors that are going to simplify out, just to remind myself and make it, it's more for a teaching thing too, but it does help remind. The next term here has a 6, and I think we're going to need to do some factoring here, right? What is 100 50 factor down to. And when I see a 0 at the end, I always just go, well, that's got to be 10 times something, right? 15 times 10. And 15 will factor down to 3 times 5. And 10 factors down to 5 times 2. Well, wait a minute. There's a perfect square, right? 5 squared times 3 times 2. Okay, and 3 times 2 is definitely not going to simplify out because it's not a perfect square. So why don't we just call that a 6? So 5 squared times 6. So 150 becomes 5 squared times 6. Now we are in the great position to realize that the power of 2 matches the index of 2, and out comes the 3. Now don't forget that we also had a 2 out there, and when it comes out it multiplies. And that's because of the product rule that I talked about before. What's left under the radical? Just the square root of 6. Ultimately, right, don't forget we got to multiply that, so this is 6 square root of 6. Now over here, once again, oh, this is great. We have a power of 2, and index is 2, so we do know that out comes a 5. And of course, don't forget that 6 there, and that gets multiplied. 6 times 5 is 30. So let's finish up what happened. What was left? Well, that 6 stayed inside the square root. So we've got 30 square root of 6. Now look at the beginning. Those were not like radicals, and they didn't even look even close to like radicals. But after doing some simplification, we find out that they are. They are root 6s. So now we have 6 root 6 minus 30 root 6. So 6 minus 30 is going to give me what? Negative 24. Negative 24 what? Negative 24 root 6s, right? That's what we're sort of collecting up and adding up. Root 6s. How many? You got 6 of them over here. You got minus 30 over there. Oh, we got a total of negative 24 root 6. Next problem, and it says assume all variables are greater than or equal to 0, so we don't have to worry about any kind of absolute value issues when we're simplifying. Any kind of negative value, negative variables that we might have to deal with absolute value is not a problem because we're assuming all variables are positive. So let's see, greater than or equal to 0, so positive or 0. Anyhow, those are definitely not like radicals. The indices are 3, so that's the same, but the radicands, definitely not the same. Okay, well, I think it's time for us to see if we can break these down. So what we want to do is we're going to want to take 16. Let's take 16 first, right? Use 16. Wait, what are we going for here? Remember, we need to know a direction. And that indice tells us that we need to find a perfect cube. So that kind of gives us a direction. Search for 3 factors of a repeating, say this correctly, a repeating factor of 3, oh my gosh, repeating factor 3 times. If I say 3 times, it sounds like 3 times something, but a repeating factor something times something times something. So I want to be clear. So now 4 factors down to 2 times 2, and 4 breaks down to 2 times 2. We actually have a repeating 2, 4 of them, right? So that makes 2 to the 4th power, but we want cubes. So why don't we just be a little clever here and write that as 2 to the 3rd power times 2. Okay, so that's what we're going to do. We've got a negative 9x. We've got a cube root. And we say look at 16 is 2 cubed times 2. Don't forget there's still an x in there. Don't forget that. And then we have 9 cube root of 2. And I think we could do something with that, right? Can't we write that as x to the 3rd power with a leftover x? That's, right, not a cube. So this sets us up to be able to simplify, right? If I see a perfect cube and it's a cube root, we'll simplify with it. Well, that 2 gets to come out. And let's for sure not forget that we already had a 9x out here, and that gets multiplied. And what stayed inside the cube root? Looks like 2x stayed inside, plus 9. Now it looks like, once again, awesome, there's a perfect cube. lines up with cube root, so x comes out, and what stays inside is the cube root of 2x. And so their cube roots and their 2x radicans, these are like radicals. Before I do that, I do want to simplify this a little bit by multiplying. Negative 9 times 2 is negative 18, and that was cube root of 2x plus 9x cube root of 2x. Well, what is a negative 18 plus 9? Well, that's negative 9x cube root of 2x. So you really had even more going on here in the way of we're looking for, let's get my color here. We're looking for like radicals, and we do have like radicals. Whoops, I lost something. Aha. Let me go back for a second. When I multiplied these two, right here, I'm right here, negative 9x times 2 is negative 18x. Whew, sorry about that. Because that x definitely has to be there, because I was about ready to explain that you had two things going on. You had like radicals, right? These guys were the cube root of 2x, but to make them like terms, the whole thing has to be identical and not, x is part of that. So really what were we collecting? We were collecting x cube root of 2x's. We had 18 of them first, negative 18 of them, and then we had 9 of what's? X cube root of 2x's. So really it was that whole thing that made it a like term, including with the like radical. Okay, but that is our answer. Blink, let's do that. Make sure you guys know that that is the full answer, negative 9x cube root of 2x. Let's go to number 12. And number 12, I left this A and B business here because this is not going to simplify. And let's see why is it not going to simplify. First of all, are these like radicals? And you'd say, well, the indices are 2, that's good. But definitely the radicans are different, so that's not good. They're not like radicals. Can these simplify down? Well, this is a 3, and it's prime. Can't simplify any further. You could say 3 times 1, but of course that's not going to go anywhere. And that's 2 times 1, and that's not going to go anywhere in terms of a perfect square simplifying out of the radical. So they are simplified. They are unlike radicals. We're going to have to say B. B, B, B. This expression is fully simplified. There's nothing I can do with that. Number 13. Subtract as indicated. Assume that all variables are greater than or equal to 0. So good. Don't have to worry about that. Okay, we got to be a little clever with this one because you cannot add because they're not like terms. They're not like radicals and they're not like indices, right? This guy over here is a square root. Okay. We're going to be a little clever here. We're going to take this in purple and write it over here and work on it. What was that? That was the 8th root of m to the 4th. So we're going to be clever and remember that we can write this as what? We can write this as a rational exponent. How'd that go again? Rational exponent? Well, the index is the denominator and the power, or the exponent, is the numerator. And that is just a fraction. What's 4/2 reduced to? 1/2. I'm sorry, what's 4/8 reduced to? 1/2. Now, can I rewrite this back? Can I change this back to a radical form? The answer is yes. There's my radicand, m. There's my power, 1, which you don't have to show a power of 1. And then there's my root index, 2. So when we go ahead and rewrite this back over here, how come that didn't work? There we go. Back over here, I'm going to rewrite this back over here as, what did I get? The square root of m. And if you want to know what's in front, right, you could always think of a 1 being in front. Okay, the other problem is, wait a minute, yeah, I think you realize that 36 is a perfect square, right? So, if we wrote that as 6 squared, you know that that power of 2 matches the index, and out comes a 6. So what is that going to be? It's going to be 6 square root of m. Now, even though it didn't look like it, didn't even look like it was close, the radicands were very different and the indices were not the same. But now the radicands are the same and the indices are the same, which means you can subtract them. 6 minus 1 square root of m is going to be 5 square root of m. And you're done. Okay, so now what? Multiply and simplify. All right, we're going to have to multiply, in this case, distribute. Now with multiplication, the rule is not the same as addition, subtraction, and it shouldn't be because they're different operations. But with multiplication, like if I said a square root of a times the square root of b, what has to be the same? Well, the radicands don't have to be the same. But what does have to be the same is your indices will have to be the same. And if the indices are the same, then you can multiply different radicands without a problem. But the index must be the same. So let's go over here and take a look. Also, I think what I want to do is bring you back to an idea. Like if let's say that was x times 4 plus minus something. What would you do when you said x times 4? Well, you just said it was 4x, right? Didn't you just write it like that? And that's the same thing you're going to do with radicals, okay? That's going to be the same thing you're going to do with radicals. So let's get rid of that. And let's go ahead and do our distribution. Multiply, right? So, and if it helps, what's in front is a 1. And we're multiplying 4. So 1 times 4 is 4. And what do we have? We have a cube root of 12. That was the first distribution. And the second distribution, now I could have, no, actually that wasn't going to simplify. So I take that, I scratch that. I wish I would edit and scratch out any slips of the tongue, but I caught myself. So we're just going to distribute. We did the first one. Let's distribute the second one. So now we've got, now what did I say? The indices must be the same, and they are. So then we're just going to multiply. So we're just going to multiply. And if you wanted to think about that 1 being in front, 1 times 1, which just gives you a 1, you can, but you don't really need to show those 1s in front. And then this is going to be the cube root of what is 12 times 2, 24. Now, if we can reduce, we must reduce. It said multiply and simplify. So 24. Is there a perfect square in 24? Oh, no, I'm sorry. We are looking for not a perfect square. We're looking for a perfect cube, right? So cube roots. Always, like I say, always important to know your indices. So what about 8 times 3? And we know 8 is just what? 2 times 2 times 2. The more you do of these things, the more they jump out at you because you're just used to seeing them. Maybe a good idea to write down perfect cubes and perfect squares, maybe even perfect fourths, just to, not all of them, of course, you can't have all of them, but I mean, have the common ones so it doesn't surprise you as much and you get quicker. Would naturally happen after you do a billion problems, but having a chart might help, or just some notes with that. Well, I'm going to rewrite this as the cube root. Instead of 24, let's write this as 2 to the third, which is 8, times 3. And that helps me to see, something. That helps me to see that the power of 3 matches indices of 3, so out comes that 2. And now we've got 2 cube root of 3. And over here, unfortunately, that 12 is enticing. Like, man, shouldn't that simplify? And the 12 would simplify if it was a square root. See, 4 times 3 is 12, and 4 is a perfect square, right? 2 squared. But we're not looking for perfect squares. We're looking for perfect cubes. And there's not the repeated multiplication of a same factor in this 12. It doesn't. There's no perfect cubes. So this is as far as this one goes. So that was what, number 14? And number 14 should end up as 4 cube root of 12 minus 2 cube root of 3. And that's what we got. Okay, now multiply and simplify. These get to be a little bit nasty. Now you do want to remember that we do have some special products that we, hopefully still remember or can go back and familiarize ourselves with them. This one is not one of those, so we're going to have to sort of painfully go through the whole extended distribution, or some people like to call it FOIL. So that is going to be 8 times 5 is 40. And then we've got, now remember, that number just gets multiplied by the number in front. So 8 times 2 is what, 16 root 5. That root 5 is being multiplied by it, so it's okay, right? It's just that that's how we show it, because these are radicals and the 16 is not a radical, but it's still being multiplied. It didn't disappear. And then we do this part right here. I guess use a different color. And don't forget the sign, negative 8. So negative 8 times 5 gives you a negative 40, root 5. And then we've got a negative 8 root 5 times 2 root 5. So do the numbers first, right? Do the numbers first. Do that. Negative 8 times 2 is going to give me a negative 16. And look at this, something you're going to want to know. This is root 5 times root 5, which is square root of 25. Now, you know that that's just going to become what? 5. But here's something to remember. When you have a square root times another square root, and this you can't have a negative under this for this to work. These have to be real numbers. And actually, I really probably should say that too, way back at the beginning, just to be technically correct. Wow, I'm just so totally lost here where I'm at. Okay, there we go. Way back at the beginning, when we did the product rule, gosh, where the heck did it go? Must have been at the beginning, I would have guessed that I said it. I know I said the product rule before, and it is, okay, this is awkward. So the thing about the product rule is that it only works for real numbers. So up there it is right there. Geez, it just popped up when I looked all over. I couldn't find it, and now I find it. So this is the product rule, right? I thought I did that a lot earlier, and it was just the previous problem. Definitely need a coffee or some kind of medication. But this says, you can see what it says, right? So the nth root of a times the nth root of b equals the nth root of a times b. But this only works, it's only for real numbers. And that's kind of like, that can get by us a bit. But it's basically saying you're not allowed to, so tell me, what's the square root of negative 16? And you're going to say not a real number. So we're not allowed to use this with numbers that are not real. So basically, if you have a negative under the radical and an even index, you cannot use this cool formula or product rule. So that's something I should have said. It's a detail that gets by us, but and it doesn't come up a lot until a little bit later in the book. It becomes more obvious because we start getting imaginary numbers. But anyhow, I wanted to go back to that because it kind of hit me a little bit. But if we have the square root of x times the square root of x, instead of going through all this extra work, why don't we just call that x, right? Because look what's going to happen. The square root of x times square root of x is the square root of x squared, and then there's that power matching the index, which means x comes out. So whenever you have the square root of a radicand times the square root of the same radicand, you can actually just drop the square root signs, because that's what's going to happen when it simplifies. In other words, when I saw the square root of 5 times the square root of 5, I know it's just going to be 5. So that can save us a little bit of time. So let's see, that was just 5. So let's zoom in a bit here and do some simplifying. So we have 40 out here. We also have some like radicals, right? Square root of 5s will go together. So what number is this? This is number 15. What is 16 minus 16 root 5, 16 root 5 minus 40 root 5? That's basically 16 minus 40, which is a negative 24 of what's? Root 5. Now we also have this multiplication problem that's happening here. And that's going to be negative 16 times 5 is negative 80. And oh, wait a minute, now we have some like terms, don't we? Don't we have some like terms? The answer is yes. So it's 40 plus a negative 80. Well, that's a negative 40. And then what do we have left? Minus 24 square root of 5. And that's the final answer. Negative 40 minus 24 square root of 5. And somebody might say, hey, oh, can I factor out 2 or 4 or a negative 8? Yes, 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 you can. But we usually just leave the problem like this when we are multiplying and simplifying. This would be considered simplified. And sometimes if you want to factor because you're reducing a fraction, that would be fine too. But in this case, this is an acceptable simplification. Let's take a look at the next problem. And the next problem, whoa, that went crazy. No, it didn't. It came back anyhow. The next problem is something special, right? Isn't that a special product? I think I'm going to review it real fast over here in my space. Special product. Well, it's called a perfect square binomial, which makes a perfect square trinomial. And remember what that was? Remember from the past. If we have a, is this plus or minus? Minus. Let's do the one with the minus. A minus b, and it's a perfect square. Yes, you can write a minus b times a minus b and FOIL to your heart's content and add in all that, combine like terms. But we do know that this is a formula that just happens over and over again. We might as well use a formula which says it will be a squared minus double a times b plus b squared, right? And so I don't have to go through all the pain of multiplying, foiling, and combining like terms. And so if you grab a hold of that, you will have the benefit, be rewarded with these problems being easier. Like watch, this is a perfect square binomial, so I'm going to say, well, that's going to be the first term squared, and that's going to be minus double the first term times the last term plus the last term, which is square root of 7, squared. Okay, well, this is easy now. 5 squared is 25. If I multiply negative 2 times 5, that's minus 10 square root of 7. And I just said when you square a square root, right? Actually, these guys undo each other, just leaves a 7. Anything else to combine? Yeah. These are just constant values which get to come together. 25 plus 7 is 32. So we end up getting 32 minus 10 root 7. Okay, that was a perfect square binomial. Oh, there's another one. And the nastier the roots get, the better this formula is because it saves us from having to distribute and FOIL all that stuff. So let's do it again. This is going to be equal to the first term squared. Once again, where am I getting this crazy stuff from? This cool formula that we looked at sections ago, right there. First term gets squared. The middle term is going to be minus double the first term times the last or the second term, which is that was just, you don't have to worry about the signs because the signs are built into the formula. So that's 6 root 2 plus the last term, 6 root 2 squared. Now all you do is just simplify. Square root of 11 squared, well, the power in the index will actually just cause it to simplify out to 11. The middle actually has, now just to be clear, everything is being multiplied here. So this is, somehow my sleeve is making this thing jump around. This is 2 times root 11 times 6 times 2. So because this is multiplication, you really just put those numbers together. So this is just going to give us a negative, 2 times 6 is 12. And of course, we also are going to multiply because they're not like radicals, but we're multiplying. They have the same indice. So we're going to say, what is the square root of 11? Let me just use another color. What is the square root of 11 times the square root of 2? Well, that's the square root of 22. And then finally over here, this is just going to be, well, what is this? This is just going to be 6 root 2 times 6 root 2. Well, 6 times 6 is 36, and root 2 times root 2 is square root of 4, which is just 2. That still gets multiplied, so it's 72. Okay, so that's where we're at. I don't know if you saw that multiplication right there. That's where we're at. Is there anything that will combine? Anything that will combine? What number is this again? This number 17. Anything that will combine? And the answer is yes. I've got 11 and a 72, right? 11 and 72, that will combine to make an 83, right? 72 plus 10 is 82, plus more is 83. So that's 83 minus 12 square root of 22. You might say, what, doesn't this simplify 22? Well, no, 22 is just 2 times 11. There's no perfect squares in there, so that will not simplify. And that 83 minus 12 root 22 is our final answer. Moving on, and we're getting close to the end, I think. Are we? Maybe not. We're getting closer, though. Of course, we're always getting closer. But now what is this? This is another special, right? Root 6 minus root 3 times the quantity root 6 plus root 3. This is called the difference of two squares. Another one that you really want to get down because life is so much easier if you know that a plus b times a minus b. What happened when you FOIL or multiply that out? Every single time, the first term gets squared, the last term gets squared. The middle stuff always is opposite, so it zeroes out, and it's a minus sign. It's called the difference of two perfect squares. And so that happens every time, and so that's going to make our life so much quicker if we just remember that. What is the first term? Well, it's just going to be root 6 squared. The middle stuff all cancels away, becomes 0, and then it's the last term, which is root 3, and that's a perfect square. Well, root 6, once again, the power is matching the index, so that 6 comes out. That power is matching the index, so the 3 comes out. And what's our final answer? 3. That was convenient, and I want to put a little star by this, because this convenience is so convenient it gets used next section. So these two guys are called conjugates of each other. Notice the root 6 minus root 3. What's its conjugate? Root 6 plus root 3. So it's just a sign change. But what that does is it makes, when you multiply them out, it makes the middle terms zero out, which was those nasty square roots, and it squares the first term and last term. And when you square perfect squares, it makes them nice integer numbers. And so guess what happened? We had these nasty radicals, and by multiplying by its conjugate, we have a nice integer value. So that's not the lesson of this class, but it will be the next on this section, but it will be the lesson on the next section. So it's good to remember that this difference of two squares business that we did in the past actually helps us a ton, because it cleans a nasty problem up and turns it into a nice rational number. Okay. Keep that in the back of your head as that comes up. And it also comes up when we're working this stuff. So what's the next one? Subtract as indicated. Assume that all variables are greater than or equal to 0. Thank you very much. Don't worry about absolute values. Okay, well, subtract. I don't think so, right? Because these this is a square root, and this is a fourth root. And this is a radican 49x, and that's just x. So as it is, they are not like radicals. I cannot add or subtract them. But if I get a little bit clever like I did on another problem, remember that? Fourth root of x squared. I temporarily turned it into a rational expression, rational exponent rather. And so this is x raised to the, remember how it works? I'll use some color. Remember how it works? The index of 4 is your denominator, and the power or exponent of 2 is your numerator. And you can clearly see that that's a fraction. 2 halves is 2 over 4 is 1/2. Can I write this as a radical? Once again, there's my radican. There's my root index. There's my power, which I don't have to show a power of 1. So all what I can do is I can rewrite that original to the square root of x. And by doing that, I really do save a lot, because we also know that 49 is a perfect square, 7 square. And so we know that that power is matching the index. Out comes a 7. What stayed inside was the square root of x. And what do we have on the outside? A 3. So now we have 3 times 7 is 21, square root of x, minus, and you might even want to think of this as what? A 1, square root of x. These are definitely like radicals. What's 21 minus 1? That is going to be 20, square root of x. And there you go. 19 is 20, square root of x. Let's look at 21. Oh, we're going to have to do some distribution. So what is that? That's going to be square root of 3. Now remember, in order to multiply radicals, the radicands don't have to be the same, but the indices do, and they are. Awesome, we can multiply them. So what is, and also remember that other piece was they have to be real numbers, and these are real numbers. So root 3 times root 5 gives me root 15, plus, what's root 3 times 15? That's square root of 45. Cannot add them together unless they're like radicals. The radicands are different. But wait a minute, will they simplify? Does 45 have a perfect square in it? And 45, isn't it 9 times 5? I believe, right? So 9 is a perfect square. So I could write it as 3 squared. And once again, when the power matches the index, out comes that 3. So square root of 45 can be simplified to 3 root 5. Is 15 going to do anything in terms of simplifying? Well, 15 is 3 times 5, and that's definitely not a perfect square. So that is it. The answer is square root of 15 plus 3 root 5. Now we're down to the last page. Assume that all variables are greater than or equal to 0. Thank you. Go ahead and distribute. And you might think, what's going on? Well, this is a 6 that's outside of a square root. There's no square root. And 2x is on the inside. So please do not multiply radicands times numbers that are not inside. So that is just multiplication, and we just write multiplication as that 6 in front. So that's no big deal, right? It's multiplication. It's also a coefficient, but that's how we can write it. On the other hand, these guys both have the same indices, so we're allowed to multiply their radicals, or radicands rather. And so this is going to be the square root of what is 2 times 10, that's 20, and x times x, that's x squared. Now we want to know, can we do any simplifying here? And the answer is yes. Why don't we, I'll take an extra step. I'm going to run out of space up here. 20 factors down to 4 times 5, and 4 is 2 squared times 5. So you do know 20 is 2 squared times 5, and x is a perfect square. So yes, there's definitely going to be some simplification happening. Power of 2, the index of 2, out comes a 2. The power of 2, the index of 2, out comes an x. What stays inside is just 5. Numbers is 21, so it just stays 5 over here. Over here we have 6 square root of 2x. Now we're looking to see, can we do more? And 6, the radical is square root of 2x, and this is square root of 5. They're definitely different, so we are done. The answer is 6 square root of 2x. I want that to go all the way. 6 square root of 2x minus 2x square root of 5. Okay, now next problem number 22. Don't see this as a special product. It kind of almost looks like it might be, but no, it's not a difference of two squares. It's not a perfect square. We're going to have to just go through our process. That's going to be 5 times 3 is 15. Then we got 5 times root 2 is plus 5 root 2. Then we've got, I guess I'll use another color. We have root 3 times 3, which is just 3 root 3. And finally, root 3 times root 2, which gives us plus root 6. Now, is there any simplification that could happen? That's supposed to be a 3. Any simplification that could happen? No. Are there any like terms? No, this is root 2, and these are root 3s. That's a root 6, and that's a constant. No, there's really nothing else I can do with this darn thing. That's it. That is done. It doesn't feel very satisfying probably, but that's it. 15 plus 5 square root of 2 plus 3 square root of 3 plus square root of 6. We're getting there. 23, we've got to go to 25. Well, this is a perfect square. Perfect square binomial. Remember the formula? Let's do it again. The formula says if you have a plus b, perfect square, that will always simplify or multiply out to what? A squared plus 2ab plus b squared. If you want to save some time, get that memorized, right? Because all I have to do is write this as a, the first term squared, plus 2 times the first term, 8, times the second term, square root of 7, plus the last term, square root of 7, squared. So 8 squared is 64. And 2 times 8 is 16 root 7. And square root of 7 times square root of 7, well, this just makes 7, right? It's the square root of 49. Square root of 49 is 7. So now we're getting there. All we have to do now is add our like terms, and our like terms would be 64 and 7. What's 64 plus 7? That's 71. 71 plus 16 root 7. And those are not like radicals, and 7 is not going to simplify any further. And there's my answer. Check. Okay? And we're down to almost last. Oh, how beautiful. We have a difference of two squares, also known as a conjugate. This guy is the conjugate of this one. So notice this, we have square root of 3 minus 8, and I've got square root of 3 plus 8. This is just going to work out great, right? All we have to do is take the first term and square it, minus the last term and square it, and just simplify. Well, square root of 3 times square root of 3 is square root of 9, which is just going to make a 3. Also, we know we could also justify that by saying the power of 2 and the index of 2, out comes a 3, right? That works too. And 8 square root of 64. And there we go. We're almost done. 3 minus 64 is a negative 61. Got it. Oh, last problem. Anything special? Yes, it is special. That is 4 plus 2 root 3 times the quantity 4 minus 2 root 3. It's the same thing as last time. It's a difference of two squares, which I tried to highlight somewhere back there a bit. Okay. Difference of two squares. So that's just going to be, my first term is 4, perfect square, minus my last term is 2 root 3, perfect square. 4 squared is 16. And I don't know if you remember the rule of exponents that says if you have a times b, and that's raised to a power, that's in this case 2, but it works for any power. It's not distribution, but it kind of feels like it. It's saying, basically it's saying everything in the parenthesis must get raised to the nth power. So it's a to the nth times b to the nth. And so this is just going to be 2 squared, which is 4, and root 3 squared, which is just 3. Okay, and so now we need to multiply this. We had 16 minus 12, which is 4. And we are done. Done, done, done. That was the last problem, I believe. 65, that's it. Okay, I hope that helped out. You guys have a great day and keep it going there with your homework. Take care. Bye.